So now to science. This is actually a morning with 3 packs. I will also talk about using population transfer in a more computer science setting, talking about parallel tempering with quantum multivariable updates. And I should credit Vadim Smilyansky, who really brought this field to the Google Quantum AI team. But then we are honored to have Boris Altschuler as the Spiritus rector behind this effort. And we have strong contributors like Kostya, who help us work this out. And then there also, I think he's sitting somewhere here, Vasil, folks who come more from the computer science side, who will wrap this into hopefully functioning algorithms. Before getting to the new ideas, I wanted to go through the history quickly. How did we get there? And that is talking about tunneling via hopping. And you may all recall that the original intuition why we think quantum annealing could offer a speed up is that if you have to traverse an energy landscape given to you by some optimization problem, that the transition probabilities to escape a local minimum are possibly enhanced if quantum tunneling plays a role. So we have this picture in mind where you want to go from A to B in thermally assisted annealing, but you don't have to go thermally all the way over the barrier, but you can chop, so to speak, part of it via a tunneling transition. And that was the original idea. And you may recall this figure from a few years ago. We demonstrated that you can put this idea to use on a machine like the D-Wave machine we had available at the time, the D-Wave 2X. And for a crafted problem that brings out this tunneling property, we were indeed able to find a significant 10 to the 8 factor speed up relative to a metropolis-based algorithm such as simulated annealing based on single spin flips. And we also found a large speed up relative to Monte Carlo. It wasn't a true computational speed up, as you may recall, because we could have used other algorithms with cluster finding abilities, and they would have done faster than everything shown here. But it showed that in principle, the idea of tunneling via hopping has merit. But the reason we got somewhat disenchanted by these seemingly positive results was that even though there was a speed up relative to quantum Monte Carlo methods, it was only a prefactor speed up, not a scaling speed up, and that's scary to computer scientists. And there was different lines of work. This is a picture from a paper by Sergei Isakov plus other members of our team that showed that in certain situations, tunneling can be tunneling by hopping, a term I learned from Vadim, can be emulated by quantum Monte Carlo in the sense that here in this study, fully connected ferromagnetic cluster was considered. And then, of course, you can model tunneling via imaginary time path integrals. But then we found if there is only one dominating path, then the scaling of quantum Monte Carlo and the scaling of quantum annealing is identical, so only prefactor speed up. And various other papers listed here, I think one from Elizabeth, I think there is also have seen similar things. However, one should say there is a whole list of obstructions preventing quantum Monte Carlo from efficiently emulating tunneling. Yeah, there are topological obstructions if you use non-stochastic drivers, but also maybe most importantly, if there's not a single dominating path, but you have to consider the interference of many Feynman paths, then quantum Monte Carlo will not suffice. And that's why we are so excited about what you heard earlier this morning from Boris and Vadim, moving from hopping tunneling, so to speak, to band tunneling. And I fear you may get sick of it by now. You have seen this picture probably now 3 times. but the advantage with me is I can only express it in very simple terms. So I will tell you the story briefly yet one more time, but then connect it to computer science. So as Vadim pointed out earlier, we are considering a situation, and I think the projector doesn't show the bands, but you have an optimization landscape as shown here, and then you're interested, of course, to find the low-lying states, to sample from the low-lying states, and if you then have states in these low-lying energy wells, then the typical driver Hamiltonian that we consider in annealing, the sum over sigma x, will not immediately couple those states. Why not? Because in a situation like a SAT problem or random energy model, if you go low enough in the spectrum and you pick a computational basis state there, the next computational basis state will be order n spin flips away. But the driver doesn't immediately couple those. So these are these little dashed lines. You have to go to an nth order process. You have to hop a number of times to connect those two states. And therefore, if you think in terms of an effective Hamiltonian, you have a battle of two exponents. One exponent is getting smaller, that is the off-diagonal elements that couple, let's say, psi I and psi j. So this tunneling matrix element will fall exponentially off, but as Vadim pointed out earlier, the further you go in Hamming distance, there are also more partner states to which you can possibly tunnel. And that battle of two exponents leads to interesting spectral features of such Hamiltonian. And essentially you have a transport through a network of resonances. And as Boris pointed out, you can also think of it as studying Anderson localization or Anderson delocalization, but not in real space, but on the Boolean hypercube. Yeah? And then to fixate our ideas a little bit more concretely, and summarizing what you already heard, if we consider band tunneling in the random energy model, for those who don't recall, in a random energy model, you have a bunch of strings, and then you assign each string an energy by drawing it from a Gaussian distribution. And then if you look at the spectrum, then you find interesting structures in there. You find these narrow bands. And these narrow bands essentially come about by, or if you study those states involved in these bands, they are so-called non-ergodic extended eigenstates. And I quickly jump here forward. I was counting on Boris showing this figure. This is one of Boris' favorite figures that sort of illustrate nicely, again, what you already heard about. If you start somewhere in a computational basis state, let's say you have only weakly, and you're somewhere lower in the spectrum, and you only weakly dial up your driver Hamiltonian strength, your gamma in our language typically, then you don't move much, you stay localized. If you crank up the transversal field too strongly, then you go all over the map, and essentially the support set of your wave function will be the entire Hilbert space. So this would be an ergodic extended state. But what is interesting to us computationally is this middle range, where you just dial up your transversal field strength to a point where you transport, but you don't go all over the map. You stay within the mini bands. And then going back to discussing the mini bands, so the mini bands are made up by these non-ergodic extended eigenstates, but then each eigenstate comes about by hybridizing a bunch of computational basis states. And if you look closer, they come from a somewhat narrow energy interval, and the size of this interval is 1 over n. And then if you want to study the dynamics, so you start with a computational basis state with energy E, and you evolve under the usual transversal field Hamiltonian, then you find that the dynamics is confined to a miniband, which means you can write down an effective downfolded Hamiltonian over the support set of these states that were involved in forming the extended non-ergodic states. Yeah? So there are computational basis states that are recruited to take part in the miniband, and there is where you transport. There's one thing that was mentioned earlier, but it might not have caught your attention. If you write down the downfolded Hamiltonian, however, there is, on the diagonal elements, you will see an energy shift, so-called self-energy shift. So the energies of the computational basis states that are recruited, so to speak, into the miniband, they come from a certain interval, the state of width 1 over n, and they wind up in this band where the transport ultimately happens. And then that leads to, for the random energy model, a situation like this. How far you spread will depend on two things. It will depend on how strong do you drive, how strong is your transversal field. It also depends on how locked in your starting state is, how deep in a local minimum. Oops. Okay. How deep in a local minimum you started. And oops. So this figure shows the situation if the transversal field is weak, and actually here up here is sort of being deep down. This is the magnitude of the energy for the random energy field model. So up here, blue means the size of your support is small. Essentially, you're stuck, you're localized. And then if you dial up for a given place in your spectrum, the transversal field stronger, then you start to form extended states. So it's this area where we're interested in. And again, you have heard this earlier, how fast do I spread in these bands? So what's the transfer time? The transfer time, the formula that you saw earlier from Vadim was more complicated, but I took all sort of correcting factors out, and essentially what you find is that the transfer type is of Grover type. Yeah, you go as square root of 2 to the n divided by the size of the support set. Yeah, so this is, with Grover speed, you spread in these mini bands. And if you go to a very specific model, Vadim and co-workers were able to work out sort of exactly how this looks. And this is sort of from a computer science model. A condensed matter physicist would call this the impurity model, which is essentially such where you have a spectrum where sort of all energies are 0, with the exception of m marked states. And I just went to the simplest case where we have only 2 marked states, a start and a final state. And I place myself in the start state. I can artificially always organize this. But again, condensed matter jargon would be impurity model. As computer scientists, we would say, oh no, wait a minute, this is a Grover problem. This is unstructured search. Your task is to find the final state starting from the start state, but you don't know where the final state is. So it will classically take you Grover time. But then to our delight, what Vadim et al. Was able to show is that using population transfer with many-body delocalized states, you find the final state in a time. Again, there are some correction factors. Ignore all this. Just stare at this. This is actually 1 over. This is a matrix element, so the time to get there would be 1 over this. But it's not 2 to the minus n, which would be the classical time. It's 2 to the minus n half. So you find the final state in Grover time. So that makes you feel good. Okay, so how do we use this resource of population transfer in minibands in a computational setting? And we think it probably best combines with a technique such as parallel tempering, which normally is conceived of as a classical technique with single spin updates. But quantum population transfer naturally gives us multivariable updates. And the idea, as you can imagine, or goes like this, is also so far population transfer is a purely coherent phenomenon. So there's no way of getting rid of energy, there's no dissipation inbuilt. So therefore, we combine it with a classical technique, parallel tempering, that provides the dissipation. So you would start somewhere in your energy landscape, you perform metropolis updates, giving you a dissipation until you are stuck. So you use the different replicas. Maybe I should quickly say, I assume most of you are familiar with parallel tempering, but just for those who are not, quickly reviewing. Parallel tempering is very familiar. I like to think of the little brother of, or the big brother of simulated annealing. In simulated annealing, it's also a metropolis-based algorithm, where you accept spin flips according to the metropolis rule. And the metropolis rule takes a parameter as input, temperature. And if temperature is high, you easily accept the spin flips. If temperature is low, you don't easily accept spin flips that lead to an energy move upwards. You always accept the spin flips going downward. But in simulated annealing, you go from a high temperature to a low temperature monotonously, while in parallel tempering, you have a stack of copies of your system, referred to as replicas, and each replica lives at a different temperature, and you do metropolis dynamics at that temperature, and then once in a while you have an outer loop that looks at neighboring replicas, neighboring in temperature, and you check the energy of the replica at the higher temperature. If that happens to be lower than the neighboring replica at the lower temperature, then these states are not compatible with their respective temperatures, so they should switch. And what this does, you essentially organize diffusion process where the low-lying energy solutions, they sink down, and the bad solutions, they percolate up. But this is an entirely classical process. So for example, I've shown this picture 2 years ago. We can nicely monitor this process. So far, this was just classical. And I can have a replica server, and I can nicely implement this in an asynchronous server architecture. And I can have parallel tempering cook away. But since this is all classical so far, I can monitor it. And then when I spot a replica that doesn't make any good progress, then I say, you come, and I give you the special treatment with a quantum processor. And then I try to elicit population transfer there. To here, jump maybe back to this. So let's say I got stuck. I noticed the replica was stuck. I elicit population transfer. I hope I travel in these bands. And then I might wind up at other energy states that are far away in Hamming distance, but not so far away in energy. And maybe I get lucky. I started out from a local minima where I was stuck. I find another energy where there's still a dissipative downward path, and then I can iterate this. And you can actually implement this either on D-Wave. Actually, that's why we pleaded with D-Wave to please change the control electronics a little bit so that you can do what D-Wave calls reverse annealing, but it was really motivated by population transfer. But of course, you can also implement this on gate matter machines, for example, by just trotterizing the evolution. And here's a way how we could do this on Google's Gmon processors, where you essentially have iterations of driver Hamiltonian, the red guys, and blue ones is the cost-related Hamiltonian. Yeah. Of course, both have limitations. If you do it on a gate model machine, you can only go for a certain number of trotter slices until you exhaust your error budget, until you exhaust the available fidelity or T1 times. On D-Wave, you would have, or in physical annealer, you would have to be careful. This is a coherent dynamic, so you would have to compare the W in your MRT experiments, so the line broadening to the width of the minibands to see whether you can observe this physics at all. So to better wrap my head around it, I made a little simulation to see how this all works. And I did a small simulation on a laptop. It was just 18 qubits. It's a fully connected random Ising problem. Here's the energy landscape projected. Here's the bit strings. Here's a 000 bit string. Here's a 111 bit string. And here are all the bit strings in between. And then here you see the energies. And then I used a metropolis-based algorithm, and I got stuck here in this local minimum. It's not the global minimum yet. So I initialize my population transfer there. So I put my wave function such that I'm with probability 1. So all population is in this trap state. And now I evolve this. Oops. So a little video here for you. So you see how the wave function now delocalizes. So you lose population here and it spreads out. And maybe I stop this here at some point. So what you see now is the wave function has spread. And if you look at these histograms here, this is a histogram of the original energies. And this is the histograms of energies I would see if I keep measuring the state. And it does what we like it to do. It essentially samples energy from the lower energy spectrum. So that's nice. We like this. And you can see also traveled some not insignificant Hamming distance in this small scale simulation. And then we continue doing simulations a little bit. Here is one with 25 qubits, but it goes to show this doesn't always work because I'm not only comparing it with random sampling from the original energy distribution. I also compare it to steepest descent, which is actually the best strategy for these small scale problems. And you see steepest descent, this is this red histogram from which you would have sampled. And if I do parallel tempering starting here at the state with the dashed line, I get a distribution here as to the green. And then I take states from my distributed states and I measure it and I take samples from it. And from these classical samples, I start steepest descent and then I get this green, this bluish histogram. And if you look on this side, you see that most of the time, actually, plain vanilla simulated annealing or steepest descent would have won. Only in one case, I got a better probability ratio this way. This is a ratio between steepest descent alone and steepest descent started from parallel tempering. But this is, of course, tiny. This is just because it's coherent. I'm stuck with small-scale simulations. So I only have 25 examples, so there are only very few minima. So I cheated a little bit or crafted a problem where I have more minima. I put some dimers in. And as soon as I do this, it looks much better. So now there are many more minima. It emulates a little bit how it would look in a larger scale. And then you see that now my SDPT histogram has higher probabilities to see the low energy states. And if you look here, you see, oh, now I have many more points above 1 where steepest parallel tempering, population transfer followed by steepest descent leads to a better probability. So you get here on a crafted problem some win. So to summarize, is population transfer, as we explained it to you this morning, this is a useful subroutine. So the pros are in small-scale simulations with crafted problems, I can outperform simulated annealing. But you may say, oh, you have been there already, that we have seen already years ago, this is not per se new, but that's the best I can do in terms of simulation so far. But we also have seen from Vadim that for the Grover problem, for the impurity model, I should say, this would have given us a Grover speed up. So we have some theoretical guarantees that in principle, this should give us a speed up. So what's worrisome? Now what's worrisome is there is a self-energy shift. So the participating computational basis states are drawn from a certain band with a polynomial width. And then the natural question is, how expensive is it to get down into this band by, let's say, restarted simulated annealing and just stopping when it winds up in this band? So how expensive in time is that? We don't quite know this. Also, for the impurity problem, even though it's true that the driver nor the time has to be fine-tuned, there still needs to be exponentially close precision with how you represent the energy level. So this has to be, either you don't travel so far, or if it's a really large problem, you probably will need error correction. But then there are also new things to try. That is, we can play with the driver variationally. We can put variational strategies on top of it. And we can add cooling qubits. So we can make this overall quantumly by not marrying it to parallel tempering, but have it an overall quantum system by adding cooling qubits. We haven't tried this yet. So I skipped the last slide, which was essentially, maybe if you permit me one more sentence. So we have Eddie Fay on our team, as you know, a co-inventor of QAOA. And we often argue over lunch, Hartmut, we should do more QAOA. And I said, no, population transfer has, to me, a better physics intuition behind it, because I understand traveling via resonances. But if you look at it, you make a little table, you find that there are actually QAOA and population transfer in certain ways is rather related, because if you trotterize it and you put it on a gate model machine, the gates you use are very similar. And even though QAOA is supposed to start with uniform superposition, there's by no means that you have to do this. You could have used a smaller subset. Population transfer doesn't have to start from a single computational state either. As I said earlier, population transfer can perfectly be married with variational ideas. That's orthogonal. So overall, these two concepts are not, they have different physics intuition behind it. So Eddie and co-workers feel good about QAOA because at least for some time they got very close or even surpassed for a while the best classical approaches. And we feel good about population transfer because it achieves the Grover speed up in unstructured search. So we have different reasons to feel good about those approaches theoretically, but again, I wanted to point out they're not entirely different. Okay, with this, I wanted to thank you.
Thank you, Hartmut. We have time for maybe one quick question.
Thanks, Stuart. Hey, great presentation and great sequence of presentations. I actually found this really enlightening. I don't know if this is more of a question, but more of a comment. I think there's a really interesting sort of thought here for the community, because I know there's some mathematicians here and geometers and things like that. The notion of searching over a hypercube, I think, is probably a more appropriate intuition for the classical algorithms, like the one that Helmut Katzgraber is talking about, or I don't know it particularly well, but moving between solutions at the bottom of an energy well. And I think what would be really useful considering here is the idea of not the Boolean hypercube, but the Ising polytope in the higher dimensionality, because in that concept, the quantum annealer is basically finding the lowest low-dimensional facet of the higher dimensional polytope, and what's giving it these faster rates for equilibrating in population transfer is that it's reducing the dimensionality of the solution space by extending its wave function across a volume of the polytope, and then it's basically moving between solutions that are within that volume. And the extent, this is what you don't get with the hypercube, because you can have two solutions that are actually low energy together, but they're on opposite sides of the Hamming space. The extent to which it basically occupies the size of that lower dimensional volume is how much you crank up the driver Hamiltonian, like how much that transverse field comes on. And I feel like that actually might make a connection between the techniques that you're describing here and the ones that mathematicians are thinking about in terms of like how to search solution spaces and reproduce distributions in machine learning and things. So I thought it was fascinating.
I think the closest to the situation you just described, I think was in Vadim's slide, where he showed sort of the block diagonal Hamiltonian, and there were sort of these colored patches of computational basis states among which you travel if you start at one of their members. So you explore sort of your ergodic, but only in a subset. And that's indeed could be a quite useful subroutine if formulated properly. Of course, you want to be sure that in this puddle of states you are visiting, the solutions you're interested reside in there.